in the book, everything is either 2 or 3 of the bottom line or independent variable, well, of the intermediate variables, and either 1 or 2 dependent variables. So most of our problems would be like this, where you have a function of 2 variables, x and y. These are what I've called second line variables in the notes. The x and y will depend on 1 or more of the independent variables that would be the bottom line, and typically the first line variable would be the one that's over here. So typically then we'd say df dt, if we're thinking of x and y as functions of t, is the partial of f with x dx dt, and since x and y depend just on the one independent variable t, then these would be straight up and down d's. So you'd have something like this. So you can see that you could rewrite this as a dot product of a vector constructed this way, consisting of the partial derivatives with x and y, dotted with dx dt, dy dt, because if you do your dot product, you'd have this times that, which is there, plus you'd have this times this one, which is here. So this is a convenient way to write things, and it also is something that gives us quite a bit of insight into what ultimately will prove to be going on, as you'll see in just a few minutes. If you have 3 variables, which we also want to be able to work with, then say you call the function of 3 variables w, and then your dw dt, you could either write it dw dt or df dt. You'd have your partial with x, dx dt, following the pattern here, partial with y, dy dt, partial with z, dz dt. And again, you can write this as a dot product of a vector that looks like this, and it has a name, which I'm about to drop on you, with dx dt, dy dt, dz dt. Because here again, if you're doing the dot product the way we've done dot products, you have this one times that, which is there. You have this one times that, which is there. You have this one times that, which is there. So we give this the name gradient, and so you can write it gradient parentheses f. And you see we're treating it as a vector, so this would be bold-faced type in the book. And we either write grad f, and so I put the line on it at the board, but it's bold-faced type in the book. And the other way to write it is with this symbol. This upside down Greek letter delta is called del in this country anyway, and the use of the symbol and choosing the name del seems to go back to Gibbs. Remember that the dot product and the cross product of chapter 12 are products of Gibbs. Well, it depends on how you want to look at it, his genius or his imagination. Depends on what you believe, I guess. Whether you think mathematics is all a game or whether you think there is truth out there to be discovered. So anyway, be that as it may, so the del n, as it's printed in the book, would be what we call it a vector operator, and so it's printed to look like a vector, which means that I had the pen there, it doesn't look right. In the wastebasket, right? Okay, so anyhow, del. And so the two component gradient then, del f would be, you could think of it this way, this is another way to write partial derivatives with the subscript, and the three component gradient then looks like that. So look at the other vector in our dot product that we use to define the chain rule. In the xy plane, r of t would define a parameterized curve, say you call it C, and if r of t is defined this way, then the velocity vector, which remember is the tangent is always pointing tangentially. Think again of the picture that we had here when we were in chapter 13 with the curves and the osculating plane, and the vector velocity is pointing tangent, like the headlights of the little car on that road and so on. So what we have here then is that the dx dt, dy dt that we've worked with here in the chain rule is our dr dt vector. In the same way, if you're thinking of a three-component vector, the corresponding dx dt, dy dt, dc dt would again be the dr dt. Say you call, when it's three components, say you used capital R for the name of the vector that's tracing out your curve, so then this would be d capital R dt. Either way, you see, you have what you have in words is that the chain rule is the dot product of the gradient and the vector velocity. You could say that as a true statement, either two component or three. So that's what I'm saying down here, that the df dt is del f, the gradient, dot v of t, gradient times velocity. So if you have a surface, I'm using the Greek letter sigma as the name of a surface. Say you have a surface like this. Notice it's similar to the one that's still on the board that we worked with last week, but that one, as you see here, is a portion of a sphere with radius 3. This has radius square root of 6. The reason for working with this one is that, as you can see, 1, 1, and 2 would be a point on the surface. So it allows me to study these various curves that we're going to talk about, all intersecting at the same point up here with coordinates 1, 1, and 2. So that helps me make a picture that shows what I'm trying to show. So that's why I've switched from the example from last week, which is still over here, that we'll work with some more, to this example. But they're both the same idea. In both cases, you have a portion of the sphere and you have these curves up on it. And the chain rule and the idea that the dr dt is gradient times velocity is going to relate to what we're trying to do over here. So anyway, we can see that 1, 1, and 2 is a point on sigma. And so you could think of parameterized curves down here in the xy plane. So C1 is the green one coming out like this, and at the point down here, 1, 1, and 0, I'm looking at the tangents to these curves that are in the plane. This doesn't have to be the unit tangent. It doesn't really matter whether it is or not. I'm looking at a vector that would point tangent. So that would be the dr dt if these curves down here are little r as parameterized curves. So this one is y equals square root of x. So as little r, it's the vector t square root t. In the long sheet of paper handout, you'll see a sketch that's related to this, but I also have one with which is more colorful, which may be easier to follow here. So I have the curve C1 like this. It's based on y equals square root of x, which then parameterizes like that. Then the companion curve, we have talked before in this class about the companion curve concept. The idea that at each point on the curve, you can calculate the corresponding z value from the appropriate formula for your surface, which in this case is this formula. And so the corresponding companion curve with the letter K is the one that's up on the, well, in this case, it would be the darker green. And so the K1 then, parameterized, would be the corresponding T for the X. Remember, this is based on the curve y equals square root of x. So if this is x, then the square root of x is the y, and then you put the t for the x and the square root of t for the y in here, and you get 6 minus t squared minus square root of t squared, which is t. So this is the parameterized companion curve. In the first line here, the curve C is the lighter green, and the companion curve is the darker green. So it's following, it goes through the point 1, 1, 2, and you can see that. For example, if t is 1, you have 1, square root of 1, and then square root of 6 minus 2, which is 2, and comes down like this. What we are going to get at, called the directional derivative, we don't really get there until tomorrow, but where we're going with this is going to give us the slope of the companion curve in the direction of the tangent to the beginning curve, the curve identified with C. So it'll give you the slope up here at the point on the companion curve for the direction being the tangent down here at the point 1, 1 for x and y of the original parameterized curve. That's a generalization of what we had last week with the partial derivative, where the equivalent of my curve C1 here would have been, for example, the line down here in the xy plane parallel to the x-axis. Then at a point like this one, which in this example over here was 2 for x and 1 for y and then 2 for z, if you come up here, your companion curve would be this one, and your partial derivative with respect to x, as we talked last week, was the slope of the tangent line for the companion curve, where the tangent line is touching the surface at the point up here on the companion curve and on the surface above the point down here where we are evaluating things. And eventually you'll see that this directional derivative is the dot product of this vector that we've learned to call the gradient, dotted with the vector that's defining the direction, which would be the tangent vector for the parameterized curve, which in this case back here would just be I. So then you have the gradient dot I, and that's just partial with respect to x. The more generalization is with situations like this, where your curves now don't have to be a straight line parallel to the x-axis or parallel to the y-axis, like these two from last week, and they don't even have to be a straight line out at an angle, like my example with curve C4. They can be curves that are curvy curves as opposed to straight line curves. And so that's where all this is going. In the same way, if you look at the curve C2 in the lighter blue, this is x to the 3/2, or if you prefer, it's y squared equals x cubed. So parameterizing the blue one, if you're using the formula y squared equals x cubed, then I think I have those backwards. It doesn't matter, but that's actually, let's see, I want to have this so that if I solve for what I'm calling y, I'll have x to the 3/2, if I solve this, this would give me 2/3, wouldn't it? So the 2's and the 3's are backwards. So it's still 6 minus the 4th power and the 6th power, but it's in the opposite order. And so then you'd get your companion curve, which is the darker blue. And again, what's called the directional derivative is going to give you the slope of the companion curve. So it's the slope of the line, like I'm holding the stick, in the direction of the tangent to the curve that's down here. So if this is the direction of tangent T2, then what I'm talking about is the slope of this stick. So I'm talking about the angle that's back here behind my hand. Then if you're looking at y equals x, C4, this would be a straight line out here, makes a 45-degree angle in here. Then the corresponding companion curve would come down like this. And again, what I'd be getting is the slope of the line like this stick in the direction of the tangent T4, which would be the direction of this line. And that would be, this would be my parameterized curve, y equals x. And so my companion curve then would be the same parameterization for x and y, and then 6 minus the squares of whatever you've called x and y under the square root sign. What we will be going after is getting the slopes of these tangents, like I'm holding the stick here for this one, out of formulas like these. We'll be doing that more tomorrow. What I want to do now is focus on doing partial derivatives that's doing the chain rule with partial derivatives. So if you look at 14.4, yes.
So will those companion curves, will the point of those make more sense tomorrow then?
Well, I hope so.
Okay.
Because I plan to come back to it, certainly.
Okay.
Yeah, we haven't really computed any of those directional derivatives.
Okay.
It's hard to know in what order to do things, because this chain rule is the basis of being able to do what I've been trying to talk about for half an hour. On the other hand, you need practice in just doing the chain rule calculations with the partial derivatives. So what I was trying to do was to introduce what the chain rule is after.
Okay.
Now I thought we'd work with practice on doing partial derivatives and then come back again after that with
Okay.
more of what it's after, which is called this directional derivative. And this thing called the directional derivative is what's going, as I was trying to show you holding up the sticks, in the case of a problem like this one, where your direction is the tangent to the curve down here. So it's the direction this stick is pointing. Then in that direction, for the companion curve at the companion point up there, you have a tangent, which would be this thing. So then you have an angle down here, and that angle is defining the slope of this tangent. Okay, so that's what we're gonna see after a while, probably not till tomorrow, is that you have two ways you can compute that slope, called the directional derivative. One is out of the parameterization that's for your third component, and the other is out of the dot product of what we've called the gradient and a vector that's down here that's specifying the direction divided by its magnitude. So it's the dot product of the gradient and a unit vector that's pointing the direction. This directional derivative concept is important in applications in other people's classes, like physical chemistry and thermodynamics, hydrodynamics, classes of that sort, say in fluid mechanics. And so that's why it's actually worth your while to learn how to do it if you're going to do engineering, physics, chemistry, that kind of class. Actually, there are applications in mathematical economics also. So meanwhile, let's practice some drill type stuff with chain rule. I see I misspelled demonstrate. Little phonetic spelling there. So problem 2 in 14.4 wants us to demonstrate the chain rule for two variables. So we have a function of xy called x squared plus y squared. And so the chain rule, if you're thinking of the one independent variable t, dw dt would be the gradient then, which again is partial of this with x as one component, partial of this with y as the other, and that's called del w. And so it's 2x comma 2y. So that comes from there. Dot dr dt. Okay, so the r is x of t comma y of t, and the dr dt is dx dt comma dy dt. So the dw dt that it wants is this dot product. So you see then it's going to be the 2x times dx dt. Well, if this is your x, then here is your dx dt. Cosine takes you to minus the sine, sine takes you to cosine. So then you have the 2x times that, which is how you get minus 2x sine. Then you have the 2x times that, which is how you get 2x times the cosine. Okay, that's the first of your dot product calculations, plus you have the second one, 2y times dy dt, and the dy dt is here, see, from here. Derivative of cosine is minus the sine, derivative of minus the sine is minus the cosine. So you have 2y times minus the sine, and 2y times minus cosine. Okay, so now you're still not finished. You see, this is dw dt, but you still have x here and there, and y here and there. And what it wants is that you get it, what we're finally going to have is that dw dt is 0. And to see this, we now need down here to replace the x in terms of sine and cosine, and the y in terms of sine and cosine. So you're going to take the minus 2x sine t and put this x in. So here we are, here's the minus 2. Now the x from here, cosine plus sine, is there, and then that's times this sine. And then you have the 2, and the x again, cosine plus sine, so that's here, and then times this cosine. And then you have to do the same thing. You have this minus 2, which you notice is common factor. And then the y, which is cosine minus sine, and then the sine, let's see, we had what we had here first was we had 2y sine t, so here's 2y sine t, and then we have the minus 2y cosine t, so minus 2y cosine t. Here's the y down here. Follow the color again, also the orange should come down to this, and then the cosine t. So if you multiply all that out, you have minus 2 sine cosine minus 2 sine square, 2 cosine square, 2 sine cosine. Okay, so that's this line. And then you do the same thing here, and then you have to add those together. And when you do, you see it all cancels out, because you have minus 4 sine cosine here, and you have plus 4 sine cosine there, and then you have minus 2 plus 2, and then you have 2 minus 2. So the thing is identically 0, which is what the problem wanted you to show. Now the other way you can do it, you see, is if you first, you see, we've found that dw dt is 0 by doing the chain rule. That is to say, we did the gradient, which is partial with x, comma, partial with y, dot, dr dt, which is dx dt, dy dt. So if you do it with the chain rule, like this, and then change everything to sine and cosine, it all collapses to 0. The other way that you could do this, and the point of the drill here, is to calculate dw dt with the chain rule, as we just did, or rewrite the original function in terms of t, that is to say, parameterize it by replacing the x in terms of t according to what you're given, and you see you're given this connection between x and t, and replace the y in terms of t according to what you're given, and in the problem you're given that y is parameterized this way in terms of t. In other words, this defines x as a function of t, and this defines y as a function of t. So therefore, you should be able to take this and square it, and take this and square it there, and add that up. That's what I'm doing down here, and write the w directly in terms of t, and then you can do that derivative. So if I take this x and I square, then FOIL that out, gives me this for x squared. I take this y and square, FOIL that out, gives me this y squared. And then I add these up. And you see sine square plus cosine square, there's a 1. Sine square plus cosine square, there's another 1. And then you have plus 2 sine cosine minus 2 sine cosine. So w is 2, and then dw dt is the derivative of 2, which is 0. So the chain rule works for this example in the sense that it gives you 0 for dw dt, either way you do it. Either following through the chain rule or rewriting the function directly as a function of t and then doing the Math 170 ordinary derivative. So that the first 4 of the homework problems, if you're doing the written homework, are things, messes like this. The homework is quite messy in this section. It isn't mathematically deep, but you got a lot of stuff, because you got all this stuff to multiply and not get lost in your algebra. Okay, so you see I'm an honest person. I've said it's a mess, and I've said it's messy. Okay, all right. But the problems are all with this idea. Now, take a look at this one. Because this has the function w of the 3 variables, x, y, and z, and then those variables depend on 2 variables, whereas, you see, in contrast here, you have a function of the x and y, but they depended on just 1 variable, t. So this had just 1 independent variable, t, and then the 2 second line variables that depended on the t. Here you have 3 of these second line variables, x, y, and z, and they don't depend just on t, but on 2 other things that are your actual independent variables, u and v. You can construct a version of the chain rule for any finite number of variables that you'd list in here, and they can in turn depend on any number of variables, although if you have something with 3 variables here, they could depend each one on 1 variable t or on 2 like this, but they're all going to depend on the same number of variables. So there's either a t or there's 2 of them, u and v, or something like that. In other words, this is all the same. There's 2 variables here, 2 here, 2 there, but they can be various kinds of formulas. Okay, and what this wants finally is the value when u is a half and v is 1. And so what it wants first is partial of w with respect to u. This is our w right here. And partial of w with respect to v when u and v are 1/2 and 1. That's another way to say what it wants, maybe. So, remembering that this is W, partial of W with respect to U, if you're using the chain rule, you'll have this same pattern. Partial with X, partial of X with U, partial with Y, partial of Y with U, partial of Z, partial of Z with U. And then there'll also be partial of W with V, which is partial with X, so that would be the same. But now you have partial of X with V instead of partial of X with U. So this and that are not generally going to be the same. The partial with X of the W, this would match that one, this would match that, this would match that, but this one doesn't generally match that one. This generally doesn't match that one. This generally doesn't match that one. So, see, in this problem, my partial with X, see, I get a Y from there and a 0 from there, and I get a Z from there. So I get Y plus Z. And then my partial of X with U gives me a 1. And then my partial of W with respect to Y gives me an X, and it gives me a Z. And my partial of Y with U also gives me a 1. So those happen to match, but that's a happen so. Then my partial W with Z would be then my, let's see, I'd get an X from here and I'd get a Y from there. And then my partial of Z with U, you see, would be from the product, so it would just be the V. So finally, my partial of W with U will be Y plus Z times 1, X plus Z times 1, and then finally X plus Y times V. So there's an X, a Y, a Z, and another Z, and then X plus YV. Then I go through the same thing with my partial with respect to V. So first of all, I want the same partial of W with X, and that would be the same. So I copied it down here. Then I have my partial of X with V, which would be 1 from here. Then I'd have my partial of W with Y. So that would be the same as it was here, the X plus Z. And then the partial of Y with V, you know, this is minus 1. And then my partial of W with Z again would be the X plus Y. And then partial of Z with V would be U. And then I collect these and I get this. And so then if you take the X plus Y, you'll see that you get U plus V for the X from over here, as it's given, U minus V for the Y from over here, as it's given, and that the V's disappear, so X plus Y is 2U. And in the same way, if you go back here, Z is UV, and then Y minus X would be u minus v, so minus 2v. So what that lets us do is write the partial of w with u. See, we can replace the x plus y with 2u, which I've done there. We can replace the 2z with uv for the z, so two of those. And the x plus y again from here, we can replace with the 2u. So finally, I've written it in terms of u and v. The reason for doing that is we're supposed to be getting partial of w with u and partial of w with v when u and v are these numbers, 1/2 and 1. So that's why I had to rewrite the partials that it's calling for in terms of u and v, so that then I can evaluate at these values. So now I can take u as 1/2 and v is 1, and so I have 2 times 1/2 plus 4 times 1/2 times 1. And so that's going from here down to here. Partial of w with u at 1/2 and 1 is this expression at 1/2 and 1, and that's 3. And then I can do the same thing with the other one. In the same way, my partial of w with v becomes this, and then I'm evaluating that at 1/2 and 1, and I get this. And this is what the book says they are. So you see, it's messy, certainly, but it's a matter of just not getting lost in all the little details. Look at 25. It wants dy dx, so this is an implicit differentiation type problem, and so are the last ones, 31 and 32. So it wants dy dx at 1, 1 when your x and y are defined implicitly by saying that they are on the curve that's defined by an equation. So that means if you were trying to use Maple to get a graph of the curve, you would use implicit plot. If you have a curve defined by an equation, you use implicit plot. If it's defined as a function, then you use plot, or plot 3D if it's more than, if you're working in a three-dimensional setting like spheres over there. Anyway, the one thing you want to always check if you have an implicit type problem is that the point they give you is actually on the curve or on the surface. And that means that your your pair of numbers, if you substitute for x and for y, should make the left-hand side add up to the right-hand side. Well, you see it does. You get a 1 there and a 1 times 1, so you have 2 minus 2. So it's a valid problem. Okay. So if you're doing dy dx then as implicit differentiation, that means that whenever you have a chain rule that would call for the derivative of your inside function to be the dy dx or y prime, you just write as the fraction or the y prime symbol, and then you solve for So we start out and we differentiate with respect to x. So we get 3x squared. Then here we get the minus 2, and then the outside function is the square, so outside prime. And then we think of y of x as our inside function. So we just write the symbol for that. And then we have product rule. So we have the derivative of x times y, plus we have x times the derivative of y, and again we write the symbol. And so we collect the terms where dy dx is a factor, as I've done here, so x minus 4y, and we take the other terms, this one and that one, across, and that's here, and then the dy dx we want is this quotient, and what I did is I made this plus and turned the signs around here, so I changed. Another way you could say it is I multiplied both sides here by minus 1. That made this plus and then 4y minus x. And then at the point that you're given, evaluate this at 1, 1, and you get 4/3. So that same procedure is in the Math 170 class, and you may remember it from there, but it doesn't hurt to go over it. I think the reason they put it in here is that problems 31 and 32 use this same approach, but now you see you have 3 variables, so you have partial derivatives. So this same concept applied for something like either of these refers now to a surface as opposed to a curve. F of x, y, z equals 0. So we'll pick that. So thinking that we have defined a surface with whatever the problem gives, for problem 31, this is what we're given, and you see you have the 3 variables. What you want are then the partials of z with x and with y at a given point. So the formulas that they give us to use are like this. The partial of z with x is minus the partial of this function of 3 variables with x over the partial of this function of 3 variables with z. And so the capital F that where I've placed the subscript means this, the 3 signs, and you're taking the partial with whatever is the subscript. So notice the point that they give you. First of all, is it really a point on the surface? Well, if you take the pi's and put them in, you have sine 2 pi, sine 2 pi, sine 2 pi. Sine of 2 pi is 0. So you do have 0 plus 0 plus 0, which is 0. So I have checked that this is valid on the surface the same way I checked that this was valid on this curve. So problems 31 and 32 are like 25 and 26, all pushed up one more dimension. And so anyway, your partial with x, then sine to cosine, and then the inside function, when you do that partial with x, you get a 1. And then there's no x there, so your partial is 0. And then sine to cosine, and then the inside function partial with x again is a 1. So your f sub x at this point would be this at pi, pi, and pi. So you notice you have a 2 pi again, and cosine of 2 pi is 1. So you get 1 plus 0 plus 1, and that's 2. And then you want partial of y and you want partial with z to use these formulas, so you might as well go ahead and get them. It's the same idea. Your partials of your sines are cosines unless your angle doesn't have a y in it, like this one, where you're going to have cosine times 0, so just write 0. And so then put in the pi's, and again you have 1 plus 1 plus 0. And third time around, it's the same game again. So your partial with x, with y, and with z at this particular point are all the same for this problem. That's a happen so of this problem and this point. And then use your recipes that they give you, and you see that you get -1 for both answers. So that isn't that hard to do, but it is the same implicit differentiation, really, of Math 170 pushed up a dimension. And what you have to be given is that these are the formulas that you use there. Okay, so let's come back to this a little bit. Well, let's come back over here. If you remember from last week, when we started talking about partial derivatives, what I had was the other handout got last week, and I hope I grabbed it quickly. So I'm talking about the one that you got last week if you were here, where there's quite a bit of discussion, and then I define the function square root of 9 minus x squared minus y squared, and then I have surface and plane A and plane B and pictures like this. Okay, now, there has to be somebody here who doesn't have this. So, I'm looking around for guilty faces. Okay. And so, if you recall what we did when we were doing this last week, you turn the page, you see a portion of this sphere, which is this one, and you see that I'm cutting into it with a plane which would intersect to create this curve, which is in the red, and more or less red anyway. And if you look at the maple, you can see the red curve of intersection in the first of the graphs of the surfaces. And that was what I called slice A. I called slice A the curve, which was space curve x as your variable, and the y was always 1, you see, and then the z. And then I have the plane that would cut this way, where the intersection would be the green curve, And if you look at the first of the maple pictures, you can see there's a green intersection curve. And again, that's what I called slice B on the first page, where I was telling Maple to do the plot structure of the space curve 2 for X, and then Y is my parameter, and then the Z value is F of 2 and Y. And so the very first Maple drawing is essentially this without the tangent plane and normal line, as I call them, being put in that first drawing. And then the partial derivative with respect to X, as we introduced it last week, is what will give you at a point up here on the surface, like 2, 1, and 2, the slope of the tangent to the surface and to this curve, which I called slice A. If I have the tangent touching that curve at this point, the slope of that tangent, which is the tangent of the angle alpha down here, is my partial derivative with X. We did that last week. And so it is also the directional derivative, which is the dot product of the gradient, which you remember would be partial with X, partial with Y, and so on, dotted with the vector that is the direction vector for the curve down here in the plane, for which this up here is the companion curve. Well, the curve down here in the plane is the straight line parallel to the x-axis over here at y equals 1. And the tangent then for that straight line is the unit vector I. So thinking of directional derivative as gradient, dot product gradient with the tangent to the parameterized curve down here over the magnitude of the tangent vector. In other words, dot product of the gradient with the unit vector, it's gradient dot I, and that's going to be partial with X, because it's the first component of the gradient, and the tangent down here is I comma 0, if you wanted to do it like that. So in the same way, for this one, if you think of your tangent, if you think of your curve, which would be like one of these named C in my picture over here, if you think of the curve as being the line parallel to the y-axis, then its tangent is, because it's parallel to the y-axis, it's like my stick, its tangent is 0, comma j. Well, 0, comma 1 if you're writing it that way, or 0i plus j if you said it like engineers. And your gradient dot that will be partial with x times 0 plus partial with y times j. So it'll be just the partial with y. And the partial with y then is the slope of this line. And it's the tangent of the angle beta, which we talked about last week. So then what we could finish with here on this picture is that if you're looking at a point up here on the surface, like 2, 1, 2, there is a line that would pierce the surface at right angles, like this, the normal line. which is my orange here, script letter L. And it's at right angles to what's called the tangent plane, which would be what I've outlined in this color of red, this kind of rose color, which touches the surface at the point where we're studying things. So we have both tangent plane and normal line that we can get the equations for. And you see, the reason that we can do this is that the gradient is always going to be at right angles to the surface. So why is that? Well, you see, what we have is we have that the df dt is gradient dotted with the dr dt, the velocity vector. Okay, and because that's essentially what the chain rule gave us. Come back to what we were doing at the start of today's class. We have our chain rule derivative is either an expression like this, which is gradient times dr dt, or if it's three variables, an expression like this we call gradient, and the corresponding dr dt. So if you're on a surface, then like either this one or this one, you can think of your surface as, say, w of x, y, z is the sum of squares equals 6, or this one, w of x, y, z is the sum of squares equals 9. Either way, it's a function of the variables equals a constant. So then your dw dt, whether it's this w or that one, doesn't really matter. If it's equal to, if the sum of squares is a constant, then, and that's your w, then dw dt is the derivative of the constant, which is 0. So what you have is dw dt is, or df dt, either way you want to say it, is the dot product of these vectors, and it's also equal to 0. Okay, so when your dot product is 0, either you have a 0 vector or they're at right angles. Okay, so what you have then is that this gradient is always at right angles to your tangent vector. So what that means is that if you're looking, say, at a thing like this, you're up here on the surface, and there's a tangent vector for each of these, the dark blue and the dark green and the violet one and the red one. And you can say that your gradient then is at right angles to those. So it's the normal to the surface. Well, that's where we're going with this stuff tomorrow. Okay? And so what I'd urge you to do, especially with the handout of my drawing, which goes with this picture, which will be here tomorrow and we'll pick up with it. You see, I've drawn in the drawing these curves, same general color scheme I've tried to follow. And you see I have my little tangents up there on the surface. And as the work shows, if you look through the back of this sheet of paper, which we'll go through tomorrow, you do any of these derivatives of the capital letter R, and you can take the cross product of two of those, and you'll get vectors that are normal to your surface, and no matter which two you take the cross product and you'll get the same thing. So that's what I have written on the back of this, and that's what we'll work with tomorrow. So we'll pick up at this point tomorrow.
Did you ever have the snap sheet?
Oh, I forgot about it, but